Herbivores, primary consumers. These animals feed directly on living plants, producers, or plant remains. They may be large or minute in size and are of following two types. 1. Benthos, which are the bottom-dwelling forms such as fish, insect larvae, beetles, mites, mollusks, e.g., Pila. E. Figure 9.2. A pond ecosystem showing its basic structural units, the abiotic inorganic and organic compounds, and biotic producers, and consumers, herbivores, carnivores and decomposers. Components. Planorbis, Unio, Lamellidans, etc. Crustaceans, etc. 2. Zooplanktons, which feed chiefly on phytoplanktons and are chiefly the rotifers as Brachionis, Asplantna, Licane, etc., although some protozoans as Euglena, Coleps, Dileptus, etc., and crustaceans such as Cyclops, Stenocyprus, etc., are also present in the pond. Besides these small-sized herbivores, some mammals such as cow, buffaloes, etc., also visit the pond casually and feed on marginal rooted macrophytes. Some birds also regularly visit the pond to feed on some hydrophytes. E. Carnivore order 1, secondary consumers. These carnivores feed on the herbivores and include chiefly insects, fish and amphibians, frog. Most insects are water beetles which feed on zooplanktons. Some insects are the nymphs of dragonflies which feed upon aquatic insects. E. Carnivore order 2, tertiary consumers. These are some large fishes, game fish that feed on the smaller fish and, thus, become the tertiary top consumers. C. Decomposers. They are also called microconsumers, since they absorb only a fraction of the decomposed organic matter. They bring about the decomposition of dead organic matter of both producers, plants, as well as macroconsumers, animals, to simple forms. Decomposers help in returning of mineral elements again to the medium of the pond and in running biogeochemical cycles. Decomposers of pond ecosystem include chiefly bacteria, actinomycetes and fungi. Among fungi, species of Aspergillus, Cephalosporium, Cladosporium, Pythium, Rhizopus, Penicillium, Thelivia, Alternaria, Trichoderms, Circinella, Fusarium, Curvularis, Polycoelomyces, Cyprillenia, etc., are most common decomposers in water and mud of the pond. Function of an ecosystem. When we consider the function of an ecosystem, we must describe the flow of energy and the cycling of nutrients. That is, we are interested in things like how much sunlight is trapped by plants in a year, how much plant material is eaten by herbivores, and how many herbivores are eaten by carnivores. Thus, the producers, the green plants, fix radiant energy and with the help of minerals such as C, H, O, N, P, Ca, Mg, Zn, Fe, etc. Taken from their edaphic soil or aerial environment, the nutrient pool they build up complex. Organic matter, carbohydrates, fats, proteins, nucleic acids, etc. Some ecologists prefer to refer to the green plants as converters are transducers, since in their view, the most popular and prevalent term, producer, from energy viewpoint is S-RNU, L.TRM, lead lung. There the dead organic matter is decomposed to simple forms by micro. Viewpoint is that green organisms. Plants produce carbohydrates and not energy, and since they convert or transduce radiant energy into chemical form, they must be better called converters or transducers. The two ecological processes of energy flow and mineral cycling involving interaction between the physico-chemical environment and the biotic communities may be considered the heart of ecosystem dynamics. In an ecosystem, energy flows in non-cyclic manner unidirectional from sun to the decomposers via producers and macroconsumers, herbivores and carnivores, whereas the minerals keep on moving in a cyclic manner. Productivity of ecosystem. The productivity of an ecosystem refers to the rate of production, i.e., the amount of organic matter accumulated in any unit time. It is of following types. 1. Primary productivity. It is defined as the rate at which radiant energy is stored by photosynthetic and chemosynthetic activity of producers. Primary productivity is of following types. I. Gross primary productivity. It refers to the total rate of photosynthesis including the organic matter used up in respiration during the measurement period. GPP depends on the chlorophyll content. The rate of primary productivity are estimated in terms of either chlorophyll content as CHL per gram dry weight, unit area or photosynthetic number, i.e., amount of CO, fixed per gram CHL per hour. E. Net primary productivity. It is the rate of storage of organic matter in plant tissues in excess of the respiratory utilization by plants during the measurement period. Primary production is measured by following methods: harvest method, oxygen measurement method, or light or dark method, oxygen diurnal curve method, carbon dioxide measurement method, enclosure method, the aerodynamic method, the pH method, radioisotope method, chlorophyll estimation method, C-1993. 2. Secondary productivity. It is the rate of energy storage at consumers' levels, herbivores, carnivores, and decomposers. Consumers tend to utilize already produced food materials in their respiration and also convert the food matter to different tissues by an overall process. So, secondary productivity is not divided into gross and net amounts. Due to this fact, some ecologists such as Odom 1971 prefer to use the term assimilation rather than production at this level, the consumer's level. Secondary productivity, in fact, remains mobile, i.e., keeps on moving from one organism to another and does not live in situ like the primary productivity. 3. Net productivity. It is the rate of storage of organic matter not used by the heterotrophs or consumers, i.e., equivalent to net primary production minus consumption by the heterotrophs during the unit period as a season or year, etc. Food chains in ecosystems. In an ecosystem, one can observe the transfer or flow of energy from one trophic level to other in succession. A trophic level can be defined as the number of links by which it is separated from the producer, or as the nth position of the organism in the food chain. The patterns of eating and being eaten forms a linear chain called food chain, which can always be traced back to the abiotic part of ecosystem. Producers. Thus, primary producers trap radiant energy of sun and transfer that to chemical or potential energy of organic compounds such as carbohydrates, proteins, and fats. When a herbivore, Decondyle animal, eats a plant, or when bacteria decompose it and These organic compounds are oxidized. The energy liberated is just equal to the amount of energy used in synthesizing the substances. First law of thermodynamics, but some of the energy is heat and not useful food chain. Energy, second law of thermodynamics. If this animal, in turn, is eaten by another one, along with transfer of energy from a herbivore to carnivore, a further decrease in useful energy occurs as the second animal, carnivore, oxidizes the organic substances of the first, herbivore or omnivore, to liberate energy to synthesize its own cellular constituents. Such transfer of energy from organism to organism sustains the ecosystem, and when energy is transferred from individual to individual in a particular community, as in a pond or a lake or a river, we come across the food chains. The number of steps in a food chain are always restricted to 4 or 5, since the energy available decreases with each step. For example, in a typical food chain of an Indian river, a diatom may be eaten by a copod, which is eaten by a small fish, which forms the food source of large fish, and so on. 1993. Fossil fuels. Scindesmus boletes greater than Brachionis falcatus, phytoplankton, zooplankton. N2. Homo sapiens 0 while ago adu less than amblypharangodon sp. Man, a large fish, a small fish, in an Indian pasture. The following food chain operates. Cynodon dactylon greater than Melanoplus differentialis, a grass species, a grasshopper. N2. Hopurozamensis mucosis less than Bufo melanostictus, errant snake, a toad. One may ask, why is the number of trophic levels in a food chain limited? In a simple food chain, Fig. 9.3, out of 1,000 calories of energy reaching a plant, only 10 calories, 1%, are stored by the plant. The remaining calories of energy, 99%, are lost to the environment or for plant's own maintenance. Of the 10 calories which are available to the herbivore, 9 calories, 99%, are lost at its level, and only 1 calorie is passed down to the carnivore. Thus, at each trophic level in a food chain, a large portion of energy is used for its own maintenance and ultimately lost as heat. Consequently, organisms in each trophic level pass on less and less energy than they receive. This tends to limit the number of steps or trophic levels to 4 or 5. The longer the food chain, the less is the energy available to the final member. Many direct or indirect methods are employed to study food chain relationships in nature. They include gut content analysis, use of radioactive isotopes, precipitin test, etc. In nature, basically 2 types of food chains are recognized: grazing food chain and detritus food chain. 1. Grazing food chain. This type of food chain, figure 9.4, starts from the living green plants, goes to grazing herbivores and onto the carnivores. Ecosystems with such type of food chain are directly dependent on an influx of solar radiation. Thus, this type of food chain depends on autotrophic energy capture and the movement of this energy to herbivores. Most of the ecosystems in nature follow this type of food chain. These chains are very significant from energy standpoint. The phytoplanktons, zooplanktons greater than fish sequence, or the grasses equals rabbit fox sequence, are the examples of grazing food chain. Further, the producer herbivore, carnivore chain, predator chain, parasitic chains also exist wherein smaller organisms consume larger ones without outright killing, is the case of the Preda _ U Tors, B 990 calories 2, detritus food chain, the organic wastes, lost to the exudates and dead matter dairy, fed from the grazi, ing food 1000 calco lorni SNB, ronment. Chain are generally termed detritus. The energy contained in this detritus is not lost to the ecosystem as a whole, rather it serves as the source of energy for autotroph group of organisms, detritivores, that are separate from RL and R. Talar %G, TZ, the grazing food chain, and generally termed as the available detritus food chain, figure 9.5. The detritus food chain is food. 9 calories lost to the environment. Represents an exceedingly important component in the energy flow of an ecosystem. Indeed, in some ecosystems, considerably more energy flows through the detritus food chain than through the grazing food chain. In the detritus food chain, the energy flow remains as a continuous passage rather than as a stepwise flow between discrete entities. The organisms of the detritus GB Kildely food chain are many and include algae, bacteria, slime as food molds, actinomycetes, fungi, protozoa, insects, mites, crustacea, centipedes, mollusks, rotifers, annelid worms, nematodes, and some vertebrates. Some species are highly specific in their food requirements, and some can eat almost anything. Many protozoa, for instance, need certain specific organic acids, vitamins, and other nutrients before they can thrive. On the other hand, the guts of small collembola, a group of tiny soil insects, have been reported to contain decaying plant material. Herbivore. Carnivore. Figure 9.3. Mode of inflow RWTG Rowya has simple food chain. Fungal fragments, spores, fly pupae, other collembola, parts of decaying earthworms, and cuticle from their own fecal casting. Hale, 1967. In contrast to the grazing food chain, in which energy storage is entirely within the tissues of living organisms, energy storage for the detritus food chain may be largely external to the organisms, and in the detritus itself. The food chain studies help understand the feeding relationships and the interaction between organisms in any ecosystem. They also help us to appreciate the energy flow mechanism and matter circulation in ecosystem, and understand the movement of toxic substances in the ecosystem and the problem of biological magnification, e.g., DDT. For details, see Chapter 14. Food web. In nature, simple food chains occur rarely. The same organism may operate in the ecosystem at more than one trophic level, i.e., it may derive its food from more than one source. Even the same organism may be eaten by several organisms of a higher trophic level, or an organism may feed upon several different organisms of a lower trophic level. Usually the kind of food changes with the age of the organism and the food availability. Thus, in a given ecosystem, various food chains are linked together and intersect each other to form a complex network called food web. Figure 9.5. Diagrammatic representation of the detritus food chain, showing energy transfers between it and the grazing food chain, as well as energy losses to the detritus food chain, after Clapham Jr., 1973. In any complex food web, one can recognize several different trophic levels. 1. Producers. 2. Primary consumers. 3. Secondary consumers. 4. Tertiary consumers. A given species may occupy more than one trophic level. The complexity of food web can vary greatly, and we express this complexity by a measure called the connectance of the food web. Actual number of interspecific interactions. Connectance equals potential number of interspecific interactions. Generalizations about food web. Generally, food webs are not too complex. As more and more species are involved in a food web, the connectance falls. Except in insect communities, omnivores are scarce, and when they occur, they usually feed on species in adjacent trophic levels. Within habitats, food webs are rarely broken up into discrete compartments. The number of species of predators in a food web typically exceeds the number of species of prey by an average of 1.3 predator species per prey species. Ecological pyramids. In the successive steps of grazing food chain, photosynthetic autotroph, herbivorous heterotroph, carnivorous heterotroph, decay bacteria, the number and mass of the organisms in each step is limited by the amount of energy available. Since some energy is lost as heat, in each transformation the steps become progressively smaller near the top. This relationship is sometimes called ecological pyramid. The ecological pyramids represent the trophic structure and also trophic function of the ecosystem. In many ecological pyramids, the producer form the base and the successive trophic levels make up the apex. Praying mantis. Thus, communities of terrestrial ecosystems and shallow water ecosystems contain gradually sloping ecological pyramids because these producers remain large and characterized by an accumulation of organic matter. This trend, however, does not hold for all ecosystems. In such aquatic ecosystems as lakes and open sea, primary production is concentrated in the microscopic algae. These algae have a short cycle, multiply rapidly, accumulate little organic matter and are heavily exploited by herbivorous zooplankton. At any one point in time the standing crop is low. As a result, the pyramid of biomass for these aquatic ecosystems is inverted. The base is much smaller than the structure it supports. Types of ecological pyramids. The ecological pyramids may be of following three kinds. 1. Pyramid of number. It depicts the number of individual organisms at different trophic levels of food chain. This pyramid was advanced by Charles Elton, 1927, who pointed out the great difference in the number of the organisms involved in each step of the food chain. The animals at the lower end base of pyramid of the chain are the most abundant. Successive links of carnivores decrease rapidly in number until there are very few carnivores at the top. The pyramid of number ignores the biomass of organisms and it also does not indicate the energy transferred or the use of energy by the groups involved. The lake ecosystem provides a typical example for pyramid of number. 2. Pyramid of biomass. The biomass of the members of the food chain present at any one time forms the pyramid of the biomass. Pyramid of biomass indicates decrease of biomass in each trophical level from base to apex. For example, the total biomass of the producers ingested by herbivores is more than the total biomass of the herbivores in an ecosystem. Likewise, the total biomass of the primary carnivores or secondary consumer will be less than the herbivores, and so on. 3. Pyramid of energy. When production is considered in terms of energy, the pyramid indicates not only the amount of energy flow at each level, but more important, the actual role the vivarious organisms play in the transfer of energy. The base upon which the pyramid of energy is constructed is the quantity of organisms pyramid of energy produced per unit time, or in other words, the rate at which food material passes through the food chain. Some organisms may have small biomass, but the total energy they assimilate and pass on may be considerably greater than that of organisms with a much larger biomass. Energy pyramids are always slopping because less energy is transferred from each level than was paid into it. In cases such as in open water communities, the producers have less bulk than consumers, but the energy they store and pass on must be greater than that of the next level. Otherwise, the biomass that producers support could not be greater than that of the producers themselves. This high energy flow is maintained by rapid turnover of individual plankton, rather than an increase of total mass. A pyramid of numbers. TC. SCTC. P. Pound S. I. Biological activities require consumption of energy which ultimately comes from the sun. Radiant energy of sun or solar energy is transformed into chemical energy by the process of photosynthesis. This is stored in plant tissues and then transformed into mechanical and heat form of energy during metabolic activities. In the biological world, the energy flows from the sun to plants and then to all heterotrophic organisms, such as microorganisms, animals and man in the following manner. Radiant energy, chemical energy, heat energy, sun, producers, consumers, metabolism, chemical, metabolism. Mechanical energy has two forms, namely kinetic or free energy and potential energy. The energy a body possesses by virtue of its motion is called kinetic energy, and is measured by the amount of work done in bringing the body at rest. Potential energy is stored energy, the energy at rest, and becomes useful after conversion into kinetic energy. All organisms require a source of potential energy, which is found in the chemical energy of food. The oxidation of food releases energy which uses to do work. Thus, chemical energy is converted into mechanical energy. Food means material containing energy that organism can use. Food is the means to transfer of both matter and energy in the living world. Plants synthesize food with the help of solar energy and inorganic substances such as nutrients, Colorado, and H0 in a biochemical process called photosynthesis. Solar energy 6CO, plus 6H, 0J, O plus 60, enzymes, etc. Chlorophyll, glucose, food. 2. Unit of energy. The unit of measurement of energy is erg. The work done in lifting 1 gram of weight to a height of 1 centimeter against the force of gravity is equal to 981 ergs. 1 crore ergs, 107 ergs, is equal to 1 joule. All forms of energy can be completely converted into heat energy. For a better and uniform expression in ecology, therefore, energy is measured not in terms of ergs but joules or units of heat measurement. Heat is measured in calories. 1 calorie is equal to the heat energy required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius, and 1 calorie is equal to 4.2 joules or 4.2 x 107 ergs. 1,000 calories 10% makes 1 kilocalories or a kilogram calories kcal or cal. Now, there is a trend of expressing energy in ecological literature in terms of kilojoules. 3. Ecological energetics. Ecological energetics includes energy transformation which occur within ecosystems. In ecological energetics, we consider I quantity of energy reaching an ecosystem per unit of area, say a square meter, per unit of time, say 1 hour, day or year, E quantity of energy trapped by green plants and converted to a chemical form, photosynthesis. And E the quantity and path of energy flow from green plants to organisms of different trophic levels of era period of time in a known area, i.e., energy flow from producers to consumers. The energy used for all plant life processes is derived from solar radiations, a fraction, i.e., about 1/50th millionth of the total solar radiation reaches the Earth's atmosphere. Solar radiation travels through the space in the form of waves, their wavelength ranging from 0.038 degree to several kilometers. While most radiations are lost in space, those ranging from 300 to 10 and above 1 centimeter. Radio waves enter the Earth's outer atmosphere, which is about 28 kilometers altitude. The energy reaching the Earth's surface consists mainly of visible light 390 to 760 and infrared component. On a clear day, radiant energy reaching the Earth's surface is only about 0.02% of the sunlight reaching the atmosphere is used in the process of photosynthesis. About 10% UV, 45% visible and 45% infrared. Green plants absorb strongly the blue and red light, 400 to 500 and 600 to 700 respectively. About 34% of the sunlight reaching the Earth's atmosphere is reflected back by clouds and dust. 10% is held by ozone layer, water vapor and other atmospheric gases. The rest, 56%, reaches the Earth's surface. Only a fraction of the energy reaching Earth's surface, 1 to 5%, is used by green plants for photosynthesis and rest is absorbed as heat by ground vegetation or water. In fact, only about 0.02% of the sunlight reaching the atmosphere is used in the process of photosynthesis. The amount of radiant energy of all wavelengths that cross unit area per unit time is called solar flux. The solar flux is about 8.368 J, 2 calories per centimeter. Min. At a given place, it varies diurnally because of the Earth's rotation on its axis. 4. Laws governing energy transformation. Energy transformation in ecosystems can also be explained in relation to the laws of thermodynamics, which are usefully applied to closed systems. The first law of thermodynamics is the law of conservation of energy, which says that energy may be transformed from one form into another but is neither created nor destroyed. If an increase or decrease occurs in the internal energy E of the system itself, work W is done and heat Q is either evolved or absorbed. Thus, A equals W plus Q decrease in the internal energy work done by the heat given off of the system by the system assigner refers to a change in quantity. The total amount of heat produced or absorbed in a chemical reaction, either occurring directly or in stages, always remains the same. This is called the specific law of constant heat sums and included in the first law. For example, combustion, a direct chemical reaction, of food release the following amount of energy. CSHO. This law explains the interconvertibility of all forms of energy but does not refer to the efficiency of transformation or conversion. In ecological systems, solar energy is converted into chemical energy stored in food materials, which is ultimately converted into mechanical and heat energy. Thus, in ecological systems, the energy is neither created nor destroyed but is converted from one form into another. Thus, when wood is burned, the potential energy present in the molecules of wood equals the kinetic energy released, and heat is evolved to the surroundings. This is an exothermic reaction. In an endothermic reaction, energy from the surrounding may be paid into a reaction. For example, in photosynthesis, the molecules of the product store more energy than the reactants. The extra energy is acquired from the sunlight, but even then there is no gain or loss in total energy. The second law of thermodynamics states that processes involving energy transformation will not occur spontaneously unless there is degradation of energy from a non-random to a random form. In man-made machines, closed systems, heat is the simplest and most familiar medium of energy transfer. But in biological systems, it is not a useful medium of energy transfer, as living systems are essentially isothermal and there are no significant differences in temperature between different parts of a cell or between different cells in a tissue. 5. Concept of free energy, enthalpy and entropy. Free energy is the component of the total energy of a system which can do work under isothermal conditions. All physical and chemical processes proceed with a decline in free energy until they reach an equilibrium where the free energy of the system is at a minimum. Ag equals A touch, where Ag equals change in the free energy of the system. A equals change in enthalpy, i.e., a change in the amount of energy in the form of heat liberated or absorbed by the system during physical or chemical changes, as equals entropy change of the system. Entropy is the name of a quantity in thermodynamics representing the degree of disorder in a physical system or the extent to which the energy in a system is available for doing work. T equals absolute temperature. Thus, a decline in G is accompanied by an increase in TAS. These are equal if there is no heat transfer between the system and the surrounding. If a reaction proceeds with a decline in free energy, we call it spontaneous. 6. Lindemann's trophic dynamic concept. As Lindemann 1942 pointed out, the amount of energy reaching each trophic level is determined by the net primary production, NPP, and the efficiency with which food energy is converted to biomass energy within each trophic step. Of the light energy assimilated by plants, 15 to 70% is used for maintenance and, therefore, is unavailable to consumers. Most herbivores and carnivores are more active than plants and spend correspondingly more of their assimilated energy on maintenance. As a result, productivity of each trophic level is usually no more than 5 to 20% that of the level below it. The percentage transfer of energy from one trophic level to the next is called both the ecological efficiency and food chain efficiency. 7. Maintenance cost of secondary producers. In general, 55 to 75% of the assimilated energy is spent on maintenance of secondary producers. Temperature, moisture conditions of the habitat and the type of species determine the maintenance cost. The drier and hotter the habitat, the higher is the maintenance cost, irrespective of species. For example, the average maintenance cost I of some Indian earthworm species was found F equals G in Keshan GO to be 6.48, 9.96 and 20.54 kilojoules per gram dry tissue. I shocked face E month in the winter, rainy and summer I. PLOGS seasons respectively in tropical pastures E. 1987. The maintenance cost varies OI. Assimilation equals seasonally and is 3 times more in some. I, L_LLL. Organic, nitrogen, containing wastes primarily ammonia, urea, or uric acid produced when the diet contains an excess of nitrogen. Assimilated energy retained by the individual organism is available for the synthesis of new biomass production through growth and reproduction, which may then be consumed by herbivores, carnivores, and detritivores. Further, not all food can be fully assimilated. Hair, feathers, insect exoskeletons, cartilage and bone in animal foods, and cellulose and lignin in plant foods resist digestion by most animals. These materials are egested either by defecation or by regurgitation of pellets of undigested remains. Some egested wastes are substances that have been relatively unaltered chemically during their passage through an organism, but nearly all have been mechanically broken up into fragments by chewing and by contractions of the stomach and intestines, which makes them more readily usable by detritus feeders. Edwards and Heath, 1963. 9. Ecological efficiency. Ecological efficiency is the product of efficiencies with which organisms exploit their food resources and transform them into biomass which becomes available to the next higher trophic level. Because most biological production is consumed, exploitation efficiency is 100% overall, and ecological efficiency depends on two factors: the proportion of assimilated energy incorporated in growth, storage and reproduction. The first proportion is called the assimilation efficiency and the second, the net production efficiency, table 9:1. The product of the assimilation and net production efficiencies is the gross production efficiency, the proportion of food energy that is transformed into consumer biomass energy. Net production efficiency for the plants is defined as the ratio of net to gross production. This index has been found to vary between 30 and 85%, depending on habitat and growth form. Rapidly growing plants in temperate zones, whether trees, old field herbs, crop species, or aquatic plants, have constantly high net production efficiencies, 75 to 85%. Similar vegetation types in the tropics exhibit lower net production efficiencies, perhaps 40 to 60%. Respiration increases relative to photosynthesis at low latitudes. Table 9:1. Definition of several energetic efficiencies. Herbivores assimilate. Prey production. Prey production. In comparison to the plant food, animal food is more easily digested. Assimilation efficiency of predatory species vary from 60 to 90%. Vertebrates prey are digested more efficiently than insect prey because the indigestible exoskeletons of insects constitute the larger proportion of body than the hair, feathers and scales of vertebrates. Assimilation efficiencies of insectivorous vary between 70 and 80%, whereas those of most carnivores are about 90%. The nutritional value of plant foods depends upon the amount of cellulose, lignin, and other indigestible materials present. Herbivores assimilate as much as 80% of the energy in seeds, and 60 to 70% of that in young vegetation. Chew and Chew, 1970. Most grazers and browsers, e.g., cattle, elephants and grasshoppers, Asami. Late 30 to 40% of the energy in their olo, atil bb or I. There is a constant movement of chemical elements of the biosphere between the organism and the environment. Biogeochemical cycles. The total mass of all the organisms that have lived on the Earth in the past 1.5 billion years is much greater than the mass of carbon and nitrogen atoms present. According to the law of conservation of matter, matter is neither created nor destroyed. Obviously, the carbon and nitrogen must have been used over and over again in the course of time. The Earth neither receives any great amount of matter from other parts of the universe nor radiant energy. Herbivore. Decomposers. Dash. Nutrients soilo RPA equals E. Docyclose significant amount of matter to outer space. The atoms of each element is carbon, hydrogen, oxygen, nitrogen, phosphorus, calcium, and the rest are taken from the environment, made a part of some cellular component of an organism and finally, perhaps by a quite circuitous route involving several other organisms, or returned to the environment to be used over again. The cyclic movements of chemical elements of the biosphere between the organism and the environment are referred to as biogeochemical cycles, after Bernadsky, 1934. Bio refers to living organisms and geo to the rocks, soil, air and water of the earth. Organic and abiotic phases of geochemical cycles. Since an element is necessary for the maintenance of life, its movement through biotic communities, organisms can be viewed in the terms of food chain. The flow of a chemical element through the food chain can be viewed as the organic phase of the biogeochemical cycle. Further, the biogeochemical cycles also include abiotic phases, which are the functions of the chemistry of the elements in question. These abiotic phases are of critical importance to the ecosystem, as the major reservoirs for all nutrient elements are external to the food chains, and flow in the abiotic phases tends to be much slower than in the organic phase. The rapidity and direction of nutrient cycling through the abiotic phases determine not only the distribution of the element in the total environment, but also its availability of living systems. There are two classes of abiotic phases in biogeochemical cycles: a sedimentary phase, which is part of all cycles, and an atmospheric phase, which is possessed by some. In some cycles, such as nitrogen, the atmospheric phase is more important than the sedimentary. In others, such as phosphorus, the atmospheric phase is essentially non-existent. In still others, such as sulfur, both phases are present and their relative importance depends on other environmental factors. Biogeochemical cycles that have dominant atmospheric phases are often called atmospheric reservoir cycles. Those whose sedimentary phase is dominant are termed sediment reservoir cycles. Types of biogeochemical CYCIES. There are two types of biogeochemical cycles, the gaseous and the sedimentary. In gaseous cycles, the main reservoir of nutrients is the atmosphere and the ocean. In sedimentary cycles, the main reservoir is the soil and the sedimentary and other rocks of the Earth's crust. Both involve biotic and abiotic agents. Both are driven by the flow of energy and both are tied to the water cycle. A. Water cycle. Living organisms, atmosphere and earth maintain between them a circulation of water and moisture, which is referred to as water cycle or hydrologic cycle. As we have already discussed in Chapter 3, water forms a very significant factor of environment, and without the cycling of water, biogeochemical cycles could not exist, ecosystems could not function, and life could not be maintained. Water is important for an ecosystem for several reasons. It is the medium by which nutrients are introduced into autotrophic plants. It is an important part of living tissue, either as liquid water or as part of essential organic molecules. It serves as a means of thermal regulation for both plants and animals. It is the medium by which sediments, a prime source of mineral nutrients, are removed from or added to local ecosystem. It covers the great majority of the Earth's surface, and is the dominant feature of all aquatic ecosystems. The hydrologic cycle is driven by solar energy and gravity. More than 80% of the total insolation that is not lost immediately as electromagnetic radiation goes to evaporate water. The atmospheric water vapor produced by this means can then condense around particles of dust in the atmosphere, often called nucleation particles. The atmosphere possesses a limited capacity for holding water vapor. Thus, the droplets formed by this means are heavy enough to fall as precipitation, under the influence of gravity. Eventually, the hydrologic cycle can be defined as an alteration of evaporation and precipitation, with the energy used to evaporate the water being dissipated as heat in the atmosphere as the water condenses. Distribution of water in Earth's surface. Water is not evenly distributed throughout the Earth. Almost 95% of the total water on Earth is chemically bound into rocks and does not cycle. Of the remainder, about 97.3% is in the ocean, about 2.1% exists as ice in the polar caps and permanent glaciers, and the rest is fresh water, present in the form of atmospheric water vapor, groundwater, soil water, or inland surface water. Nace, 1967. The rate of cycling between surface and atmosphere is very rapid. The amount of water vapor in the atmosphere is sufficient, on the average, to cover the entire Earth total of 2.25 centimeters. But the average annual rainfall for the Earth is about 81.1 centimeters. Huron, 1967. Ondine. Some place site ranges up to 1200 cm. This means that the average turnover time for atmospheric water is about 11.4 days, or that the equivalent of all the water vapor in the entire atmosphere falls as precipitation and is re-evaporated more than 32 times per year. Evaporation and transportation. Evaporation. 5. If we compare the annual evaporation and precipitation over land and sea, we find that relatively more water precipitates on land than evaporates from land. This is fortunate from the point of view of terrestrial organisms. Even so, the amount of rainfall on the open ocean is proportionately greater than that on land, taking into account the relative percentages of the Earth's surface covered by land and sea. Nature of hydrologic cycles. The hydrologic cycle over the oceans is extremely simple. The water is evaporated from the surface of the ocean and water vapors form the clouds which when cooled down precipitate the water as rainfall. But several routes are open to precipitation that falls on land: direct evaporation, transpiration, entry of water into groundwater system, and runoff. Consequently, the routes of hydrologic cycles on land can be divided into following three main categories: the rapidly cycling portion, or evapotranspiration, which includes the evaporation and transpiration; the less rapidly cycling water, or surface runoff; and very slowly cycling groundwater that seeps into the soil can end up in any one of these three categories. 1. Evapotranspiration. Evapotranspiration includes evaporation and transpiration. Evaporation refers to water that is evaporated directly from any surface other than a plant, such as a lake, soil surface, or animal skin. In most cases, the main effects of direct evaporation are to moderate the temperature of local area and to allow the hydrologic cycle to continue. In some ecosystems, evaporation also leads to a concentration of salts in the water of soil, which may be a critical environmental factor. Transpiration is water that evaporates from the surface of leaves of plants. Transpiration acts to move the biogeochemical cycles for all mineral nutrients that enter the food chain via the roots of plants. 2. Surface runoff. If transpiration is related to the mechanism of nutrient uptake, the gross movement of soluble and solid particles in the ecosystem is accomplished largely by runoff. Nutrients that have accumulated in sediments or soils can be eroded by streams and removed altogether from a local ecosystem, or soluble nutrients may be carried by soil seepage into surface waters, where they are removed from the area. Streams may carry sediment particles which can be chemically altered through additional weathering so that the nutrient elements they contain may be utilized by organisms. Finally, moving water acts as an agent of erosion which removes soil and allows weathering of the underlying rock to make their nutrients available to plants. 3. Groundwater. Groundwater is water that saturates either sediment or rock below the water table. In general, it is not trapped by plants for transpiration and it is too deep to be directly evaporated from the soil surface. It is an exceedingly important reservoir for water which moves from one place to another under the influence of gravity. The area where the net water movement is from the surface into the groundwater systems is termed a catchment area. Areas where groundwater reaches the surface and runs off are termed springs. A rock body through which groundwater flows is called an aquifer. A well drilled into an aquifer that has sufficient hydrostatic pressure to force water up into it is called an artesian well. The hydrologic. The area where the net water movement is from the surface into the ground. In general, it is not trapped by plants for transpiration and it is too deep to be directly evaporated from the soil surface. It is an exceedingly important reservoir for water which moves from one place to another under the influence of gravity. The area where the net water movement is from the surface into the groundwater systems is termed a catchment area. Areas where groundwater reaches the surface and runs off are termed springs. A rock body through which groundwater flows is called an aquifer. A well drilled into an aquifer that has sufficient hydrostatic pressure to force water up into it is called an artesian well. The hydrologic cycle on land, thus, includes evapotranspiration of water from Earth's surface and leaf surface, formation of clouds, precipitation, surface runoff plus accumulation of water as groundwater, return of water to sea via streams or direct evaporation and cloud formation, and so on. B. Gaseous cycles. Atmospheric ERLC oxygen. Body cells. Therefore, for the protection from toxic effects of molecular O, cells possess the cellular organelles called peroxisomes which mediate oxidative reactions resulting in the production of hydrogen peroxide which in turn is used through the mediation of other enzymes as an acceptor in oxidizing other compounds. The major supply of free oxygen which supports life occurs in the atmosphere. There are two significant sources of atmospheric oxygen. One is the photodissociation of water vapor in which most of the hydrogen released escapes into outer space. The other source is photosynthesis, active only since life began on Earth. Because photosynthesis and respiration are cyclic, involving both the release and utilization of oxygen, one would seem to balance the other, and no significant quantity of oxygen would accumulate in the atmosphere. However, at some time in the Earth's peroxisomes history, the amount of oxygen introduced into the atmosphere had to exceed the amount used in the decay of organic matter and that tied up in the oxidation of sedimentary rocks. Part of the atmospheric oxygen represents that portion remaining from the unoxidized reserves of photosynthesis, coal, oil, gas, and organic carbon in sedimentary rocks. The amount of stored carbon in the Earth suggests that 150 x 10 degree G of oxygen has been available to the atmosphere, over 10 times as much as now present, 10 by 10% degree G. Johnson, 1970. The main non-living abiotic oxygen pool consists of molecular oxygen, water, and carbon dioxide, all intimately linked to each other in photosynthesis and other oxidation reduction reactions, and all exchangeable in such compounds as nitrates and sulfates utilized by organisms that reduce them to ammonia and hydrogen sulfide. The cycling of oxygen is very complex. As a constituent of CO, it circulates freely throughout the biosphere. Some carbon dioxide combines with calcium to form carbonates. Oxygen combines with nitrogen compounds to form nitrates, with iron to ferric oxides, and with many other minerals to form various other oxides. In these states, oxygen is temporarily withdrawn from circulation. In photosynthesis, the oxygen freed is split from the decay water molecule TH. Is oxygenous then atmospheric, green plants reconstituted into water during plant carbon dioxide respiration, build CO into organic. Antony, mal respir, ation. Some carbon dioxide Colorado, found in the atmosphere and dissolved in the waters of the Earth. During photosynthesis, carbon from atmospheric Colorado is incorporated into the production of the carbohydrate, glucose, CH0, that subsequently may be converted to other organic compounds such as polysaccharides, sucrose, starch, cellulose, etc., proteins and lipids. All the polymeric organic compounds containing carbon are stored in different plant tissues as food and from them the carbon is passed on to the trophic levels of herbivores or phytoparasites, or retained by the plant until it serves as food for decay organisms, viz., decomposers. Some of the carbon is returned to the atmosphere or the enveloping aqueous medium in the form of CO, a byproduct of plant respiration, in which a considerable portion of glucose is oxidized to yield Colorado, H, O and energy as follows. 1/6 C, H, 0, plus O, equals Co, plus H, O plus energy. The Co, which is released as a byproduct of plant respiration is again used by plants in photosynthesis. This is the basic carbon cycle which is simple and complete. Decomposing microorganisms are important in breaking down dead material with the release of carbon back into the carbon cycle. Similarly, carbon taken up by herbivores or phytoparasites may travel a number of routes. It may be incorporated into protoplasm, assimilation, and stored until the organism dies, whereupon it is utilized by decomposers. It may be released through animal respiration. It may serve as live food for other organisms, or finally it may be stored in the environment as CO. Similar fates await carbon at the carnivore trophic levels. In fact, all the carbon of plants, herbivores, carnivores and decomposers is not respired but some is fermented and some is stored. The carbon compounds that are lost to the food chain after fermentation, such as methane, are readily oxidized to carbon dioxide by inorganic reactions in the atmosphere. As for the storage of carbon in sediments due, straight as deposition works to store materials, erosion may uncover them, and inorganic chemical weathering of rock can oxidize the carbon contained there. Some carbon is permanently stored in sediments and not uncovered by weathering. It may be replaced by carbon dioxide released from volcanoes and other similar examples of intense geological activity. In modern age, man has greatly increased the rate at which carbon is passing from sedimentary form to carbon dioxide. The combustion of fossil fuels is a significant means of recycling sedimentary carbon much faster than natural weathering. Small portion of carbon, especially in the sea, is found not as organically fixed carbon, but as carbonate CO, especially calcium carbonate kako. Kako is very commonly used for shell construction by such animals as clams, oysters, some protozoa, and some algae. Carbon dioxide reacts with water to form carbonate in the following three-step reaction. CO plus H, 0 and H, CO, and H plus HCO, and carbonic acid bicarbonate carbonate. The precise amount of each of these constituents in the water depends on the pH of the water. Organisms such as clams can combine bicarbonate or carbonate with calcium dissolved in the water to produce calcium carbonate. After the death of the animal, this calcium carbonate may either dissolve or remain in sedimentary form. Certain control mechanisms are inherent in the carbon cycle. The rate of carbon utilization is dependent on its availability. If excessive amounts of carbon are taken up in any one phase of the cycle, other phases of activity may be inhibited or slowed down. For example, if the pH of water is alkaline, more carbon is tied up in a carbonate and less is in solution. This removal of carbon in solution would upset the equilibrium established between the atmospheric and the dissolved Colorado, and the net effect would be a movement of CO into solution until equilibrium was reached. Peculiarities of carbon cycle. Though carbon cycle exhibits basic similarity with other biogeochemical cycles, yet it is unusual in that the organic phase is not essentially a complete cycle within itself. The organic biotic and atmospheric abiotic phases, however, are so closely intertwined that the rapid cycling typical of the organic phase is present. The multiplicity of paths along which carbon can flow is typical of biogeochemical cycles in general, and provides a well-buffered system with adequate feedback mechanisms to ensure an adequate supply of the carbon. It is significant that all phases of the cycle yield carbon dioxide at some time, and carbon dioxide is the raw material for them. Thus, despite its relative low concentration in the atmosphere, 0.03%, carbon in a form in which it can be used by living organisms is virtually always present. 3. The nitrogen cycle. Nitrogen is an essential constituent of different biologically significant organic molecules such as amino acids and proteins, pigments, nucleic acids and vitamins. It is also the major constituent of the atmosphere, comprising about 79% of it. The paradox is that in its gaseous state, N is abundant but is unavailable to most life. Before it can be utilized, it must be converted to some chemically usable form. Tobos biologically, the free molecular nitrogen has to be fixed and fixation requires an input of energy. In the first step molecular nitrogen, N, has to be split into two atoms, N, 2N. The free nitrogen atoms then must be combined with hydrogen to form ammonia, with the release of some energy. 2N plus 3H, 2NH. This fixation comes about in two ways. One is by high-energy fixation such as cosmic radiation, meteorite trails, and lightning that provide the high energy needed to combine nitrogen with oxygen and hydrogen of water. The resulting ammonia and nitrates are carried to the earth in rainwater. The second method of nitrogen fixation, which contributes about 90% of fixed nitrogen of Earth, is biological. Some bacteria, fungi, and blue-green algae can extract molecular nitrogen from the atmosphere and combine it with hydrogen to form ammonia. Some of this ammonia is excreted by the nitrogen-fixing organism, and, thus, becomes directly available to other autotrophs. Some of these nitrogen-fixing organisms may be free-living, either in the soil e.g., bacteria, azotobacter and clostridium, or in water e.g., blue-green algae, nostoc, calothrix and anabaena, and produce vast quantities of fixed nitrogen. In other cases, certain symbiotic bacteria of genus Rhizobium, although unable to fix atmospheric nitrogen themselves, can do this when in combination with cells either from the roots of legumes e.g., peas, beans, clover and alfalfa, and of other angiosperms such as Alnus, Ceanothus, Shepherdia, L. agnes and Murica, or from the leaves of African genera of Rubiaceae and Pavida. The bacteria invade the roots or leaves and stimulate the formation of root nodules or leaf nodules, a sort of harmless tumor. The combination of symbiotic bacteria and host cells remains able to fix atmospheric nitrogen, and for this reason legumes are often planted to restore soil fertility by increasing the content of fixed nitrogen. Nodule bacteria may fix as much as 50 to 100 kilograms of nitrogen per acre per year, and free soil bacteria as much as 12 kilograms per acre per year. Further, both free soil bacteria, azotobacter and clostridium, produce figure 10.5 root nodules of a legume plant. A. Legume root with root nodules. Ammonia is the first B, Ts. Of root nodule. C. Single cell of nodule. D. Nitrogen-stable product and like-fixing bacterium, Rhizobium. The symbiotic bacteria, they require molybdenum as an activator and are inhibited by an accumulation of nitrates and ammonia in soil. Recently, certain lichens, Calmatuniform and Peltigra rufescens, were also implicated in nitrogen fixation. Henriksen, 1971. Lichens with nitrogen-fixing ability possess nitrogen-fixing blue-green species as their algal component. Nitrogen fixed by symbiotic and non-symbiotic microorganisms in soil and water is one source of nitrogen. Another source is organic matter. The nitrogenous wastes and carrion of animals are degraded by the detritus organisms. Nitrogen is converted to the amino form, e.g., L-alanine. The amino group, NH, is liberated from organic molecules to form ammonia. This process is called deamination. Certain specific bacteria, most notably of the genus Nitrosomonas, can oxidize ammonia to nitrite, NO, by the reaction 2NH plus 30, 2NO plus 2H, 0 plus. This reaction